geometric alignment, one that does not serve navigation on Earth, gradually oriented satellites outward instead of focusing coverage downward. Engineers at multiple control centers paused and asked the same question: why would a navigation network designed for Earth suddenly redirect its attention toward deep space? To answer that, we have to understand what happens when you connect multiple satellites into a coordinated array. Individually, each satellite is limited, but together they can act as a distributed sensor system. When synchronized precisely, they can function like a single massive instrument. This principle is already used in radio astronomy, where distant antennas work together to observe objects with extreme resolution. What happened next suggests that this exact principle was applied only on a global scale. The GPS, Galileo, and BU networks, once separated by design, were now behaving as one unified system. Their signals were no longer isolated. They were overlapping, reinforcing each other, creating a coherent structure. At this point, the data stopped looking like navigation telemetry and started looking like observation output. Ground receivers began detecting new types of signals embedded within the standard frequency bands. These signals were not related to positioning or timing. They carried structured information, high-density data streams that resembled imaging output. In simple terms, the satellites were no longer just helping us navigate Earth, they were showing us something. And what they were showing was not random. The incoming data resolved into a three-dimensional mapping field. It wasn't a static image. It was dynamic, updating in real time. Objects within the inner solar system appeared with clarity far beyond our existing tracking capabilities. Small asteroids previously undetected were suddenly visible. Solar wind patterns became sharply defined. Even minor gravitational fluctuations were being visualized with precision that current instruments cannot achieve independently. This is not an incremental improvement. This is a leap. A system designed for navigation had just been transformed into a planetary-scale observation network. Now pause and consider what that means. No upgrades were installed. No human commands initiated this transformation. And yet, within minutes, our global satellite infrastructure was repurposed into something far more advanced. But the most important detail wasn't the quality of the data, it was the focus. All streams, all calculations, all processing power were converging on a single coordinate. Every satellite in the network was aligned toward one specific region in space. Not a planet, not a known object, but a point, a precise location between Earth and the Moon. This point is known in orbital mechanics as a Lagrange point, specifically L1. It is a position where gravitational forces balance in such a way that objects can remain relatively stable. It is not unusual for spacecraft to be placed there. But what is unusual is the sudden and unified attention directed toward it. At the exact moment the system locked onto that coordinate, the data sharpened even further. Resolution increased. Signal strength intensified. It was as if the entire network was preparing to observe something with maximum clarity, and then the readings changed. A new object entered the field. It was not previously tracked. It did not appear in any catalog. It was not detected by traditional radar systems before this moment. Yet, according to the newly formed satellite array, it was there small, fast, and moving directly into the L1 position. What makes this even more difficult to explain is the timing. The satellites were already aligned before the object became visible through conventional means. That suggests the system wasn't reacting. It was anticipating. The object itself showed clear signs of controlled motion. It wasn't drifting like space debris. It was decelerating. Its velocity decreased in a controlled manner, consistent with propulsion rather than passive movement. That alone separates it from natural bodies like asteroids or comets. So now we have a sequence that cannot be ignored. First, an external signal synchronizes our global satellite network. Then it repositions that network into a unified observation system. Finally, it directs that system toward a specific location where an unknown object arrives exactly on schedule. Each step builds on the last. Each step shows intention. At this stage, scientists are no longer debating whether the event is real. The data is consistent across multiple independent systems. The question has shifted entirely. It is no longer about how this is happening, it is about why. Why synchronize our satellites? Why improve their accuracy beyond human capability? Why turn them into a telescope? And most importantly, why show us this object? One possibility is that this is a form of communication, not through language, but through demonstration. Instead of sending a message we might not understand, the system is guiding us to observe something directly. It is using our own tools to present information in a way we can verify ourselves. Another possibility is less comfortable. The synchronization may not have been for our benefit. It may have been necessary for the event that is unfolding. Precise timing is critical when dealing with high-speed objects in space. If an interception, alignment, or interaction is required, even a tiny error could lead to failure. By correcting our systems, the external signal ensured that everything would occur with perfect accuracy. In that context, the GPS update begins to look less like assistance and more like preparation. And now, as this object continues to stabilize at L1, one more detail has emerged. It is not silent. A faint signal has been detected, weak but structured, and the only reason we can detect it at all is because our satellite network is now tuned to the exact frequency needed to receive it. The system has been calibrated, the alignment is complete, the signal is active, and whatever this object is, it isn't waiting for us to respond, it is waiting for us to understand. If you want to follow what happens next, make sure you stay with the channel, because what comes after this may change how we define contact itself. If everything you've seen so far feels like a controlled sequence, then what happens next removes any remaining doubt. Because the moment that signal from the L1 object became detectable, the entire situation crossed the line from observation into direct interaction. Up until now, we could argue that the system was guiding us, preparing our instruments, helping us see more clearly. But the signal itself proves something else entirely. It proves that whatever is out there knows we are watching, and more importantly, it knows exactly how we listen. The first recordings of the signal came through ground-based receivers that were already connected to the now synchronized satellite network. At first, engineers assumed it would be noise random fluctuations caused by interference or background radiation. But within seconds of analysis, that assumption collapsed. The signal wasn't random. It had structure, it had rhythm, and most critically, it had repetition. Repetition in a signal is not a small detail. In physics and communication theory, repetition is one of the clearest indicators of intentional encoding. Natural sources like pulsars can produce periodic signals, but those patterns are consistent and predictable based on known astrophysical behavior. This signal did not match any known natural pattern. Its intervals were irregular, but not chaotic. That distinction matters. Irregular patterns can still carry information if they follow an internal logic. As data continued to stream in, analysts began isolating segments of the signal. What they found was something that immediately caught attention across multiple research centers. The signal contained sequences that resembled binary encoding distinct high and low states arranged in clusters that repeated with slight variations. This is the foundation of digital communication. It is how computers transmit data, how satellites send instructions, how every modern system exchanges information. Now pause and consider the implication. A previously unknown object appears at a stable gravitational point, and within minutes, it begins transmitting a signal that mirrors the basic structure of human-designed communication systems. That is not coincidence. That is compatibility. But it gets more precise.